Hi, in this video, we want to take a look at multicollinearity when we're fitting logistic regression models. All right, so the concepts here really are a copy and paste of multicollinearity with simple with regular linear regression. And the same concept applies, the same problems come up, and frankly, these come across with all types of machine learning models. Now, the more data I have, the less of a problem this will be in real life data. I'm going to show like worst case scenario situations here where really things are nearly perfectly correlated with each other, like really, really close. All right, so multicollinearity is the idea that I have redundant predictor variables, and that redundancy will cause problems with my model. It will make my model unreliable. It can make it overfit, and it can make it so I can't trust the estimates that I get. All right, so multicollinearity is when two or more predictor variables in a model are highly correlated. Now, when I say highly correlated, it's not just the two variables correlation aspect. It's a more general point of view on this. So the idea here is, let's say I have three predictor variables, and this predictor variable can be approximated very well with these two. Like if I was to take a linear I was to take two coefficients, multiply these two, and then get this one over here, then we have high multicollinearity. And so it can be harder to spot. When we use correlation, we can spot any pairs. If I have a predictor variable here, predictor variable here, and they're highly correlated, then it's pretty obvious that I've got redundancy with these two. But if these two, if I can nearly get perfect correlation with a coefficients times these two to get this one over here, then I have multicollinearity, and that's a problem because this guy is redundant to these two. I don't need all three of them. I want to get rid of at least one of them. And we will improve model performance, model accuracy, computation time will be less. It'll be easier to interpret on every front possible. We will be better off if we have the redundant predictor variables kicked out. All right, so first and foremost, let's go ahead and just remind ourselves of what is our model structure for logistic regression, and where I have predictor variables times coefficients, predictor variable, coefficient, and so on. And this, along with the intercept, is equal to the log odds of the probability of success given the predictor variable values. All right, and we're trying to estimate the P, which is the expected value of the 0, 1 representation when the X values are the given values. All right, so multicollinearity is really well understood in the context of linear regression because that's all like a lot of matrix algebra, a lot of linear algebra going on there. And it's pretty obvious, pretty clean. And it's a very one-to-one relationship, very obvious if you've done linear algebra on like a proof level. We don't have as clear of a connection when we have logistic regression. Logistic regression, the same concepts come up, but we don't have as precise of a representation of what's going on. So really what we usually do, we take the point of view of linear regression, we study it there, and then we just kind of understand that it applies to other situations. And so here, I'll go ahead and generate some stuff. I'm not going to get into like the fine details of it, but I'm going to show things via code so that we have a better idea of what's going on. All right, so why is multicollinearity a problem? And this is true for linear regression or for logistic regression or any machine learning model. All right, so first and foremost, we'll have inflated standard errors. And so what this is saying is that I can't, like the variability on my coefficients will be so large that I really can't trust what I get from my coefficients. And so this is just driving at the idea that I want to narrow down the predictor variables I have to like an elite, very valuable, very informative predictor variables. Now, the unstable coefficient estimates, this really goes along with the inflated standard errors. Think of standard errors as standard deviations for a statistic. For this particular situation, This is the standard deviation for the coefficients. Well, if I have a large standard deviation, then I have a lot of variability. And so that means that my coefficient estimate could potentially vary quite a bit if I change like one row of data. If I was to omit a row of data, maybe I would get wildly different coefficients. Maybe, maybe not. When we have this inflated standard errors, we don't know what's going to happen. So, multicollinearity increases the standard errors of our coefficients, which make it so that we can't really trust the coefficient estimate. So we've lost the ability to make an inference off of our coefficients. Also, multicollinearity, when I have a whole bunch of predictor variables floating around, they're highly correlated with each other, and I go to make an interpretation, it gets a lot harder. So imagine I had a situation where I have someone's height and their shoe size as predictor variables. Well, I can't say directly as somebody's height increases that the coefficients are going to lead to the coefficient or the interpretation we would usually want, because as someone's height increases, so does their shoe size. And so I would need to really simultaneously consider, if I'm interested in increase in height impact on the target variable, I have to consider the increase in height, and I have to consider the resulting increase in shoe size, which together would drive the change in the target variable. So a lot of things are going to be happening when I've got redundant predictor variables. So we want to get redundant predictor variables out. Also, we're going to have reduced predictive power. This goes along with overfitting. What's going to end up happening is that when I've got multicollinearity, my model is going to be really, really sensitive to slight fluctuations in the data. And since it's sensitive to slight fluctuations in the data, I can't trust it for actual predictions. There's always a difference between the data I have on hand and the population I actually want to make predictions on. And when I overfit my model, what's going to end up happening is that it's really fine-tuned to that data, and I'm going to lose actual predictive accuracy. And because of that, we're going to have a worse model than I would have if I kicked out some predictor variables that were redundant. And then the model overfitting, that's exactly what the reduced predictive power. I have overtuned to my training set, and I can't really use my model to anticipate the future, at least if I want a good representation of the future. Also, we can create bias in our estimation. And so that instability can also just shift what I would expect to have happen. And so really, there's just a lot of problems with having multicollinear predictor variables. And these issues come up in any type of machine learning model. And so when I'm fitting a model, really the best thing to do is to get rid of redundancy if I can. Now, there are techniques like lasso and ridge that will help address these problems, but honestly, it's better to just get rid of redundancy than to let an algorithm adjust for you, because even if I don't have a reduction in prediction, it's still redundant. It's going to increase computation time, and it's going to make it harder to interpret. So in general, we want as small as possible, best predictor variables that I can get, instead of having some extra redundant junk floating around. All right, so let's go ahead and run through an example. And so I'm pulling in piping, and I'm making sure I don't get blasted in the face with digits on numbers, avoiding scientific notation, clearing my workspace. And I'm going to use the SA heart for chronic heart disease as my target variable for logistic regression. And this is from the Elementary Statistics Learn package. And for data prep, I'm converting family history to dummy variable representation. All right, so now what I'm going to do, I'm going to go through and I'm going to create horribly correlated predictor variables. The goal here is to show you what it looks like when things go wrong. So that way, I'm hoping that down the road, when you're building a model, you go, hey, this looks like that bad situation that Dr. Smith showed me. I need to hit the brakes, and I need to make adjustments. I need to make sure that I'm building a quality model. All right, so let's go ahead and do that. So what I'm going to do, first I'm going to take the rescaled version of my predictor variables. So here, what I'm doing, I'm taking the predictor variables and I'm subtracting off the column mean divided by the column standard deviation. So all columns here at this moment in the code have mean 0, standard deviation of 1. All right, so now it's going to work out that R actually is smart about redundant predictor variables. If there's a perfect correlation, it actually won't even consider it in the model. It will actually kick out the later predictor variables that have redundancy in them. And so what I'm going to do here on this chunk of code, I'm going to add just a little bit of variation, just a tiny, tiny bit to keep things pretty correlated. Not perfectly correlated because on this step in the code, the columns in scale M are perfectly correlated with the ones, the original predictor variables. And here it's just a little bit off, close but not perfect correlation. And then just to kind of add a little bit of multicollinearity aspect, because I want you guys to see like multi-dimensional correlation, not just two variables that's correlated. I want you to see more than one. I'm throwing in as correlated of a binary column as I could possibly get with this. And so for each predictor variable in the original data set, I'm going to have the original, I'm going to have the rescaled with just a little bit of bump, and then I'm going to have the most correlated binary column I could get. So each time for each original predictor variable, there's 3 floating around. And then I'm going to put them all together. So here is the original. Here is the rescaled version with the random uniform added on. And here's the most correlated binary columns I could possibly get. All right, so now let's go ahead and fit our model. I've got the model that uses the full data set here. I've got the model that uses the multicollinear predictor variables going on here. All right, now, first thing I want to do, I want to show you the problem with the coefficients. Watch what happens. All right, so here first and foremost, so I want to show, like, we'll check out what happens with the intercept. The intercept goes from -6 to over 3,000. Boom, that is an explosion of the values. That's a huge increase. That's nuts. That's nuts. Oh, and by the way, honestly, I feel like I should reduce the full regular model. I feel like I could get rid of some, a predictor variable because we got like obesity and adipose tissue. Those definitely are redundant with each other. Cholesterol maybe could get kicked out, but I'm going to just leave everything in for now because I'm trying to show you like things going off the rails. All right, so now let's look at systolic blood pressure. So here's the original coefficient. So here's what it would be without the redundant predictor variables in there. It goes all the way up to practically 5. But now look at the scale, the rescaled version. It's more negative than 200. And then here, this one's actually not nutso, but it's not helping the situation. And so you can see that things are definitely like just way, way off from where they were with the original model. Tobacco, we see the same thing. We see 0.08 going to -5, and then I've got just about -80 with the almost perfect correlation version. And it just keeps on being the same story as we go down. And you'll notice that frequently things are canceling out, like we have opposite signs. That's to be expected. Typically, what you are going to see is that you'll see like a positive and negative, and on the exact data set that I trained my model on, they're going to end up like canceling each other out on the individual predictions. Now, it's not exactly perfect, canceling out. And the reason for that is because we have correlation with other predictor variables that, the systolic blood pressure will be correlated with adipose tissue, correlated with obesity. All of the predictor variables are somewhat correlated with each other, so I don't get that perfect canceling out. But you can see that this got big, this got negative, and there's kind of like a canceling out to balance it out to be able to get the exact value on my training data. Adipose tissue is 0.02, then negative 30, positive 125. Check that out. Then family history, let's call that just 1. This goes to over 100, more negative than negative 150. I mean, check this out. Look at the huge difference. And it's just every single time as I go down the line. All right, so scale age, it got an NA. All right, so here, what happened was that scale age is so correlated with age and other predictor variables that R said, hey, I'm not even including this. I'm going to protect you from doing something extremely bad. But you'll notice that this is pretty far gone, that I can't rely on R to save me. We have to save ourselves in the situation. We need to protect ourselves from multicollinearity. All right, so how do we detect multicollinearity? So the first and foremost way that we're going to do this is we're going to look at pairwise correlations and see if I see pairwise correlation. If I see a strong correlated value, that's an indication that I only want one of the two predictor variables in that correlation. Now, that doesn't tell me about that multicollinear aspect. Multicollinear, that might be that this predictor variable here can be perfectly represented with these 5 or nearly perfectly. And if these 5 can nearly perfectly represent this one in using like a linear regression model, that means that this is redundant when I have these 5 already in my model. And so in that situation, it's harder to pick up. We're going to rely on variance inflation factor for that one. But our first line of defense is correlation. Look for the pairs. We'll do variable clustering also to try and protect ourselves. We'll do correlation plots, which does the two time. And we can also do clustering on that. And then we'll use variance inflation factor. And so basically, we're going to start with the one that's mathematically easiest, the easiest to interpret, and then progress from there to the more complicated ones. All right, so here I'm going to do a pairs plot. So here, this is the original data that I've got. And you can see, here are my correlations. Nothing's too crazy going on. Now, there is a little bit here. There. Okay, so here's a 0.6 between age and adipose tissue. Let's see, anything else greater than that? All right, tobacco and age. Yeah, that doesn't surprise me. Adipose tissue and cholesterol. All right, that's worth noting. Age and cholesterol. So, okay. Oh, here's a big one. Obesity and adipose tissue. Yeah, that's definitely the biggest one at 0.7. So that's when I see a 0.7 for correlation, that's that's my personal cutoff where like it's big. So like that's a huge issue there. All right, so anything greater than 0.7, I start really focusing in on that. So we definitely would want to remove at least one of these predictor variables from the model, adipose tissue or obesity. And so the pairs plot also can kind of show us what's going on. We can go here, and like here visually, that is what 0.7 correlation approximately looks like. And we can see the distribution of the predictor variables, down this line. All right, so now what I'm going to do, I'm going to show the same plot, but I'm only going to show it for the adipose tissue predictor variables. Why? Because it's just going to be too much to look at. It's going to overwhelm everything. Everything will have to be super tiny if I do the entire thing. If I was working on a real project, I would actually probably put this on PNG and then zoom in and work through individually. All right, so here, when I have the rescaled, you can see, even though I changed the scaled version of adipose tissue, it looks like up to rounding, it's perfect correlation. It's not, because I know that I did the random uniform aspect. But here up to rounding, it's perfect correlation. All right, and here we can see that the binary version is also highly correlated, but not severe. And so we can see like here, this is what perfect correlation looks like, straight line. And we can see the pretty decent jump on the binary connection also. Now, this is binary data, so it doesn't make sense to have this curve, by the way. Really, I would want to have something like a bar plot, but I didn't worry about it because I just wanted to run. Now, the correlation matrix is also a way that we'll protect ourselves. We saw the correlations in the upper right-hand corner of the pairs plot originally. And so, for example, we can see the obesity and adipose tissue right here is right where we saw it before. Now here, let's look at that submatrix, and we can see exactly the same values we saw before of the perfect correlation, and darn strong correlation between these. Okay, and a variable will always have perfect correlation with itself. So having one on the diagonal is not a big deal. This is the correlation of adipose tissue with itself, correlation of rescaled adipose with itself, correlation of binary adipose with itself. It's always going to be perfect one. That's not interesting. Now the correlation plot, here we can do, we use this for two different things. First and foremost, I can look for collinear predictor variables. And also I can run clustering as a variable clustering process with this. And I like to use hclust for this. Typically, I'll change this to wards D for this purpose, but I left it on default, which is complete linkage. Complete linkage is a good substitute for wards D. Wards D squared would try to minimize variance. Wards D minimizes standard deviation. Complete linkage, like two things don't come into the same group until we're like really, really confident they belong in the same group. And that's why it's by far the one most used in science. It's good for establishing like a taxonomy. And so here we see cholesterol, adipose tissue, and obesity are in a group together. Here we have systolic blood pressure, tobacco, and age in a group together. We have type A personality and alcohol are off by themselves. And so here, this gives me a hint that possibly I would actually just want to have 4 predictor variables in here, one representative here, one representative here, and then type A and alcohol. Now, another option, if I want to reduce down what's going on, is that I could do principal component analysis on cholesterol, adipose tissue, obesity, and then instead of having all of these guys, just take the first principal component. And another option would be to take systolic blood pressure, tobacco, age, and either have a representative, or I could do principal component analysis on the 3 and take the first principal off of there. And now here's a correlation plot on just the adipose tissues. And look at that, boom, perfect correlation. And over here, this is pretty decent correlation. That's what the ellipse shows. So if the ellipse looks like a circle, I've got no correlation going on. If it is that the ellipse gets squeezed down to a straight line, I've got perfect correlation. Now, variable clustering, we can create a pseudo distance metric off of this by taking 1 minus the correlation squared between 2 predictor variables. And my opinion is that instead of using r squared, we should use the absolute value of this. So r, the correlation is always between -1 and 1. Y squared is going to get shrunk down. And I find that in practice, in actual use, squaring shrinks it down too much. I would want to have the absolute value. It's what I feel is better. But by far, this is a more common way to go. There's more theory around it. If you want to do hypothesis testing, there's some tests that involve this metric. So whichever one you use, both are good. Whatever works for you. So this gives us a pseudo way of calculating distance between 2 predictor variables. If I get a distance, then I can do hierarchical clustering. And so here I'm running hierarchical clustering. I'm using complete linkage again, just because it's the default. I typically use for application at work, I usually either use single linkage or wards D, one of the two. And so now here we see really what we saw before in the correlation plot. We see that adipose tissue and obesity are together. Then we have cholesterol coming in next. Here on this part of the dendrogram, we have tobacco and age, and then we have systolic blood pressure, and then we have type A and alcohol coming out over here. Now, this does not indicate if it's a positive or negative correlation. This just says, hey, these are more correlated with each other than other combinations. And so here, what this is showing is that I might want to consider removing one of these two predictor variables. I might want to consider removing one of these two. These two are coming together pretty high up, so I probably don't want to combine them. I want to look at where predictor variables come together low to decide on what to remove. So this presentation shows me that if I'm going to remove something, I would remove one of these two first. Then after that, my next selection would be to remove age or tobacco. And now as I go up, see, because of the height of where they combine. Now, if I was going to remove another one, I would remove predictor variables so that I would have only one of these three. And then I would only have one of these three if I was to continue trimming down the model. That's what this dendrogram says we should do for that. All right, and so now let's say I'm going to go and I'm going to do this, but I'm going to do it with a highly correlated predictor variables. Well, you can see, boom, every single time we're seeing the three together over and over and over. It's a very redundant presentation. I'll also notice I did row means on all of the columns just to get like an additional redundancy in there. I'm trying to like break this. I'm trying to show you something bad. And so, oh, and family history is here. That's, binary. And so, yeah, it doesn't make sense to use the binary on that. Well, I just ran the code automatically. But you can see that I've got redundancy across the board. I would be removing either the original or the rescaled version of each of these every single time if I was to use this dendrogram to guide me on removing predictor variables. So where they come in together is an indication of when they should be removed. And you can see that real low on the dendrogram, we see the highly correlated ones coming in. And that if I wanted to continue removing, I would move up higher on the dendrogram to find where do we have redundancy. Now, variance inflation factor, what this is going to do, this is going to be the way that I find predictor variables to remove, because they're highly correlated with a combination of other predictor variables. All right, so it's in the car package. Now, I want to say, do not load the car package onto your machine. It pulls in other packages that will mess up your system. I've had this problem several times. If you're going to use things from the car package, use double colon notation like I did here. Don't actually use library car. Don't use require car when you're doing this. It's one of those few times that R does like really dumb stuff. Python does this type of dumb stuff like all the time. It's the bane of my existence at work, let me tell you. And these types of issues are why I feel like R is superior to Python. I use Python every day at work, by the way. I mean, like that was, yeah, the last 2 days was nothing but Python. It's good at some things, but it does some stuff with packages, modules that they make it harder than it needs to be. All right, so the variance inflation factor. The higher the variance inflation factor, the more it is correlated with a combination of other predictor variables. All right, so adipose tissue is the most correlated with the potential combinations of the other predictor variables. And so what's second? Obesity, I can see it as 2.6. This is, if I was to do regression with adipose tissue predicted by these, and I was to do regression with obesity predicted with all of the others, including adipose tissue, then adipose tissue would end up being a better regression model. And because of that, adipose tissue is the most redundant of all the predictor variables. And so if I want to remove something, this is saying that this one is the one to remove first. And so now, if I want to further trim my model, if after I remove adipose tissue, I need to rerun variance inflation, because when I run the variance inflation, this obesity is being impacted by the adipose tissues. And so because of the correlation between them, this value is going to change quite a bit. And so right now, this is saying like obesity would be second to remove, but once I get rid of adipose tissue, that number is going to change. Now, let's say I had to keep adipose tissue in no matter what, then I would be looking to remove obesity, would be my top one. I would like to have like I had a professor tell me that 3 and above, you want to trim it off. I don't know what the best rule of thumb is, but this is, if you sort it and you look at the extremes, you'll always be, pointed towards the one to remove. Remember, if you trim down your model, get rid of a predictor variable, you have to recalculate the variance inflation factor. You have to recalculate coefficients. You have to build the entire model over again. Fortunately, this type of model is not too difficult. Now, here, if I want to try this with the multicollinear version of what's going on, it just won't even do it because the correlation between the predictor variables and the rescaled and the binary versions is so strong that it throws an error. Like, stop it. Don't do stupid things. All right, so also we can look at the condition number. So here we're looking at the eigenvalues that we get from this, and we're looking at the codiagonal. Now here is the original version as we go down here. And notice the one that's most important is right here. And so this is showing as I get more and more predictor variables in there, I've got more of a condition. And so this is indicating I might want to remove something. All right. And we can see adipose tissue here. We can see obesity here. And so there's different interpretations of like when to remove something. But, basically the work that we've done so far, we know which one we have to remove. When I do this for codiagonal, so notice that here, this is 37. And I've got a little bit of multicollinearity. I could remove something that's at 37.55. Now look at what we got here. Look at that number. That is insane. That is crazy what we've got going on. Like, that is so huge. This is grossly bad. We need to start kicking out some predictor variables hard and heavy now. All right, so into the video. For homework, I want you to build a model and just take your predictor variables, and you can reduce it down if you want. And I want you to go through these diagnostics. Now here, I want you to build a model that you feel like would work really well, and then go through these diagnostics, check to see, should I remove something? Should I keep it? It ends up being a subjective decision on what I should keep, what I should kick out. Also, in real life projects, you're going to have constraints of like maybe your stakeholders absolutely insist on keeping collinear predictor variables. Maybe you legally have to. I've been in the situation for human resources models that I had to keep predictor variables that were redundant. Just because I can't explain all this stuff to a judge and a lawyer. To be able to defend this, I have to basically look at an academic paper and say the academic paper is 100% correct. They did it this way, therefore we're doing it this way. And that there was a precedent established, and that's what we're doing. So it's kind of like a case law justification for my model instead of solid statistics. Whatever. All right, so go out, build your model, check that your model is, check it, evaluate it, and, post it on Canvas. That's all I got for you. Life is short. Do math.